My friend, you're going to spend way more time debugging than actually writing OpenGL code. It's kind of true in general with programming, and it's even worse with 3D graphics. The GPU is a huge black box, and step-by-step debugging, well, it's going to be quite a challenge compared to C, C++, Python, Java, you name it. So in this video, I'm going to share a few debugging methods and hacks that can potentially make your life easier when it comes to 3D programming. Let's get into it. The first method is also the simplest one to use, and that's the function glGetError. This mechanism is very old, having been introduced way back in 2004, so it should be widely available. The OpenGL runtime maintains a very large state machine in the driver. If you use an OpenGL function incorrectly, it will most likely be detected by the driver, and an error flag will be set. In many cases, this error won't cause the driver to crash in any way, but there is a very high chance that your program won't function as expected. Therefore, it's very important during development to make sure that none of the logic paths in your code is causing an error to be flagged. The OpenGL specification defines a rather small set of possible error conditions, and the OpenGL runtime maintains some kind of a Boolean flag for each error, and will set a flag to true on the first encounter with the corresponding error condition. Subsequent error conditions will not be detected unless the error flag is cleared, which you can do by calling glGetError. This function returns the macro glNoError, which by the way is a 0 when there is no error, and one of the error codes when there is one. Note that multiple error flags may be set if you haven't checked for errors in a while, which is why it is recommended to do that as often as possible. Calling glGetError will return a single error code in no predefined order and will reset the flag back to false, so a future call to glGetError may detect the same error code again. The following error codes are available: GL invalid enum, invalid value, invalid operation, stack overflow and underflow, out of memory, and invalid framebuffer operation. There are also context lost and table too large that require enabling a couple of specific OpenGL extensions. Most of these errors are pretty self-explanatory. You can check the documentation for more details. In order to actually use glGetError, I recommend creating a utility function, such as glCheckError that you can see right here. This function performs a while loop until all the error codes that glGetError returns are exhausted. For each error code, we print the corresponding error string, followed by some text that indicates the function, file, and line number where the call to this function originated from. At the end of this function, we exit if an error was actually encountered. Note that the exit check is enabled only if the macro exit on glError is set. You can define this macro somewhere in your code, as in this example, or using your build system. The actual call to glCheckError is done using another macro, which in my case, because I'm lazy, is called GCE, short for glCheckError. Note that the function, file name, and line number are fetched from the standard __ variables that are available in C and C++. If the macro check glErrors is not defined, then GCE is set to be nothing. This can be useful for your final product or whenever you want to test the performance of your game without any unnecessary overhead that the error checking code may incur. We're now ready to start using the mechanism. You can place this macro after each OpenGL function call, or even on the same line where it is a bit less annoying. If it's too much, you can place it at the entry and exit of selected functions. Whatever makes sense to you. The second debugging method is more advanced than the previous and requires a minimum of OpenGL version 4.3, which was introduced in 2012. This method is called a debug output. Essentially, you provide a callback function to OpenGL, and this function gets called automatically by the OpenGL driver whenever one of the selected error conditions is encountered. This saves you from the ugliness and tedious work of placing glGetError calls all over your code. Let's see how to set it up. This method depends on the windowing system, so I'm going to demonstrate it on both FreeGLUT and GLFW. Up until this point, I've used FreeGLUT exclusively, but GLFW seems to be more popular these days and better supported. I'll do an in-depth tutorial on GLFW in the future. We start by telling the driver to create a debug context. Without a debug context, the driver may decide not to generate any debug messages. In GLFW, we do this by calling the function glFWWindowHint with the parameters glFW OpenGL debug context and true. In FreeGLAT, we need to add the GLAT debug bit to the mask that is provided to GLAT init context profile. I have to say that on my machine I was able to get debug messages even without this flag, so not sure if this is a driver bug or a FreeGLAT bug. For both windowing systems, I recommend creating the debug context and enabling debug output only under compile or runtime flags so that you won't enable debug output on your final product. At this point, you may choose to specifically request at least a 4.3 context. In GLFW, this is done with another call to GLFW window hint to set the major and minor version context flags. In FreeGLAT, you need to call GLAT init context version with the same values. This part is optional, and the windowing system may create a modern context regardless of whether you request it or not, but this is something to check in case anything goes wrong. Note that all of this must be done before the actual window is created, because the context is created along with the window, so all the flags must be set by that time. Once the window has been created, we should probably make sure that we got the debug context, and we do this by querying for the context flags using glGetIntegerV and checking whether glContextFlag debug bit is set. Again, in FreeGLAT, the bit was not set even though debug output worked correctly, but in GLFW, the bit was set only in response to the corresponding hint. The next step is to enable GLDebug output. You may optionally decide to enable synchronous output as well. This means that all calls to the callback function will be done before the OpenGL function where the error was triggered returns. This makes it easier to check the call stack in a debugger and identify the failing OpenGL function. If you don't enable synchronous output, the driver may call the debug handler concurrently by multiple threads as well as delay the call to some point after the failing OpenGL function has already returned. It's probably better to enable synchronous output unless you know exactly what you're doing. The next step is to register the callback function using glDebugMessageCallback. The second parameter is optional. This is a pointer that we can provide to some user data. When the debug function is called, the same pointer will be provided back to us. This may be useful for storing various application level stuff, but at this point we're not using it. The next function call, glDebugMessageControl, enables us to control the amount of debug output that we're going to get. The last parameter indicates whether to filter in or filter out this subset. True to filter in and false to filter out. The first three parameters filter the source, type, and severity of the message, respectively. If the value of one of these parameters is GL_don't_care, it means that it won't be used for any filtering. Otherwise, only messages that match the value will be filtered. The source of the message may be the OpenGL runtime itself, the shader compiler, the windowing system, a third-party library, or the application itself. The error type may be a general error, deprecated behavior, performance issue, and a bunch of other problems. The severity of the error is similar to what you are probably familiar with various logging mechanisms. The fourth and fifth parameters allow you to filter specific message IDs that match the source and type. This is simply a pointer to an array of error IDs and the length of the array. If you're using this feature, make sure the source and type are not GL_don't_care and that they match the error IDs in the array, and set the severity to GL_don't_care. The callback function is pretty straightforward. It receives the source, type, ID, and severity of the message. There is also the message text itself and the length of that string. The last parameter will be the value you provided when the callback function was registered. As you can see in this example, we are simply printing the names of the parameters as well as the message. The next method is to use an external tool. It should come as no surprise that the industry came up with various development tools that help in debugging the 3D APIs as well as analyze the performance of games and applications. There are free and open source tools such as API Trace and RenderDoc, as well as commercial products such as NVIDIA Nsight and Intel GPA. Each of these tools would require at least one session on its own, so in this video I'll just give you a very brief overview of the main features of API Trace, which is the tool that I'm currently most familiar with. After you install API Trace, you capture a trace of your application. The trace is basically a log of all OpenGL calls state changes, as well as the contents of all objects such as buffers, textures, and frame buffers. This trace can now be loaded into API Trace GUI, where you can replay the application and investigate each frame. We can see the API Trace GUI right here. On the left-hand side, we have a log of all OpenGL function calls, separated by frame. For each function call, we have all the parameters. We can double-click a frame or a function call, and this will replay the entire log up until this point and open up the OpenGL state on the right-hand side. This state, of course, was the current state of your program at that specific point in its execution. The first tab shows you the current OpenGL state. This is quite a long list, so by clicking on Only Show Non-Defaults, you can filter in just the attributes that you have modified. You can now inspect the values and make sure everything is as expected. The next tab shows you the shader text that is loaded for each stage in the pipeline. The Surfaces tab is extremely useful. Here you can see all the active textures as well as the frame buffer that you are rendering into, the depth buffer and the stencil buffer. If your frame is composed of multiple draw calls, as most frames are, you can actually see how the frame buffer is generated step by step. You can also zoom in and inspect stuff down to the pixel level. As you hover over the pixels, you can see the RGB values in the case of colors, or a floating point value in the case of the depth buffer. You can right-click and save each buffer as an image for offline processing. The next tab is also very useful. This is where you can inspect the values that have actually been loaded into the uniforms and compare them to what you can print on the CPU side. The display of matrices is not the most user-friendly, and I was actually not even able to see the entire matrix since the line was too long. Just remember that API Trace displays matrices in column major order. The next tab will show you the vertices that are going into the vertex shader using their shader names. Very useful if you suspect that something is screwed up in your vertex layout. The last tab is for shader storage blocks that I still haven't covered in my tutorials. As I'm working on this video, I'm thinking that this tool should probably be introduced to newcomers to OpenGL as early as possible in their curriculum. This can save people countless hours of debugging time. I hope to cover this in a future video. Okay, anyone who ever got the dreaded black window of death in OpenGL must raise their hand right now. Yeah, you too, come on, you can't fool me. When that happens, you need to remember the first rule of OpenGL debugging. No, not that one. What I really wanted to say is, this means that first, you need to make sure to get the correct coordinates of the primitive, and I'll assume a triangle here, from the vertex shader to the rasterizer, before you start checking stuff in the fragment shader. It sounds trivial, but it is important. In this example, I was trying to quickly put together a textured cube demo and got a black window. Based on the geometry first rule, I went ahead and set the frag color output variable of the fragment shader to a constant color. And here's the cube. If you still get nothing, it means that the rasterizer is not getting the XY coordinates in the -1 to 1 range, or the Z coordinate is outside of the 0 to 1 range. If you have backface culling enabled, go ahead and disable it for now. The coordinates could be okay, but the triangle might be facing away from you. The next step is to check the position of the camera and the object. Place the object directly in front of the camera and check if you can see it. If that doesn't work, start disabling any matrices that you may have applied in the vertex shader. Get rid of the view matrix first, then the world, and finally the projection. If you get to the point where you disable the projection matrix, be very careful about the coordinates. The projection is the process that maps any coordinate in the view frustum to the -1 to 1 range. A useful hack in this case is to manually set the Z component of GL position in the vertex shader to something safe, like a half, and the W component to 1. This is what the cube looks like in this case. If that doesn't work, then you need to take a good look at how you initialize the vertex buffers. Make sure the data layout is okay and all the required vertex attributes are enabled. By the way, you can even bypass the vertex buffers altogether by placing the coordinates directly into the vertex shader as a global array and access them using the built-in variable GL vertex ID. This variable is incremented automatically by the system on every execution of the vertex shader, so you just need to make sure to call one of the draw commands with enough vertex count. Okay, so we are back at the textured cube sample. In this case, it looks like the coordinates are okay because we can see the structure of the cube. This brings us to the next method. Yes, we can use the frame buffer as a poor man's debugger by outputting intermediate results from the fragment shader. This is as close to step-by-step debugging that we can get to without external tools. In this fragment shader example, the total light factor is calculated and then multiplied by the color which is sampled from the texture. We can start by outputting the light factor alone. As you can see, there is a minor contribution from ambient lighting, and there is some diffuse color that goes around the cube. This is because the light source travels around the cube in a circle. It looks okay, but if there was a problem here, we could go deeper and write out the position of the light source. This requires a bit of mental work to decipher. When the color is red, it means that the light is on the right-hand side, and when it's blue, it is directly behind the cube, somewhere along the z-axis. The color is interpolated between these two as it goes along the circle. It's never green because the y in this case is always 0. Another option is to output the normal vector, and this one looks okay as well. The green points up, the red to the right, and the blue at the back of the cube. The lighting calculations in general looks okay, so this must be a problem on the texture side. Let's write out the texture coordinates and everything looks fine. What about the actual color which is sampled from the texture? Aha! Looks like no texture is bound, so sampling is practically disabled. At this point I went back to the application side and eventually found out that the model file was missing its material file. This means that no texture was loaded. After fixing it, everything worked correctly. Okay, the next method improves upon the previous one. We can actually read back the values from the frame buffer into a standard buffer on the CPU side. It's probably simpler to see the intermediate values of the fragment shader as numbers rather than colors. This also allows us to run various algorithms such as searching for specific values or even save the results to an image file. The simplest way to do it is to prepare a large enough buffer to store the contents of the frame buffer. In this case, I've multiplied the window width by the height and then by 3 because we will read the frame buffer as bytes of RGB. At the end of the render loop, we have a call to glReadPixels. This function reads the contents of the frame buffer. The first 4 parameters specify the rectangle that we're going to read. In this case, we start at the bottom left corner and we read the entire frame buffer. The next 2 parameters specify RGB format in bytes. The final parameter is a pointer to the buffer for the result. After the call to glReadPixels, we have a simple example of a nested loop that goes over the buffer and prints values that are different than 0. You can also save the contents of the buffer to an image file by calling stbi_write_png. This function takes the file name, width and height of the image, the number of components per pixel, a pointer to the buffer, and the length of a single line in bytes, aka stride. If you don't know how to use the STB image library, then check out my tutorial on texture mapping. I'll put a link in the video description below. In order to use this function, you will need to get the header stbimageWrite.h. It's available on my Git repo, and I'll also put a link to the original location in the video description. This file should be included in a CPP file, so I've added it to the same file where stbimage.h is already included. Last but not least, make sure to define stbImageWrite implementation before the include so that the implementation will actually be compiled. There are more advanced usages of rendering into an offline render buffer that I'll cover in a future video. That's it for today. I hope that at least some of this material will be useful to you in your OpenGL adventures. If you have your own special debugging methods, then you are more than welcome to share them with the community in the comments below. Thank you very much for watching, and I hope to see you in the next tutorial.